Hello everybody and welcome to my 11th video. This is on Ternary, T-type and JK flip-flops. I'll be going through the binary implemented design of these flip-flops. First of all, we'll start with the T-type flip-flop and the characteristic equation Q plus equals Q plus T modulo 3. This equation was derived in my previous video on base NT and JK flip-flops, and this is a truth table of T, Q and Q plus ternary signal variables there and the binary variables here of the flip-flop. So Q plus equals T plus Q, so 0 0 equals 0, 1 0 equals 1, 2 0 equals 2, 0 plus 1 equals 1, 1 plus 1 equals 2, 2 plus 1 equals 0, etc. All the bottom way to the bottom, and 2 plus 2 equals 4, which is 1 modulo 3. Now I'm going to implement the ternary T-type flip-flop with two binary JK flip-flops, hence the excitation table for the binary JK flip-flop, and the coding of the ternary variables T, Q and Q plus are here for T, T2 and T1 are the binary codings, Q2 and Q1 are the binary codings for Q, Q2 plus and Q1 plus are binary codings for Q plus. So Q plus is the value of Q after the flip-flop has been clocked, and the variable T follows the coding 0, T2 equals 0, Z1 equals 0, T equals 1, T2 equals 0, T1 equals 1, T equals 2, T2 equals 1, T1 equals 1. That's the binary coding for T. For Q plus, it follows the same coding. If Q plus is a 0, Q plus 2 is a 0 and Q plus 1 is a 0. If Q plus is a 1, Q plus 2 is a 0 and Q1 plus is a 1. And if Q plus is a 2, Q2 plus is a 1 and Q1 plus is a 1. Now for Q plus, Q2 and Q1 are the outputs from the binary JK flip-flops, and they follow this coding here, which has an extra state in it. So this normally would be this one 0 0 0 1 and 1 1 for 2, but I've got an extra state of 1 0 here, which is a logic 1. Now this is because Q1 and Q2 could start up in any of these combinations, and because of this we have to take this state into account. So Q plus here is a 1 when Q is a 1, and this doesn't follow this characteristic equation. So what I've done is I've arranged, if Q starts up in a 1 0 here, then on the next clock cycle Q2 and Q plus 1 go to a 0 1. Then on Q2 and Q1 follow the set pattern here without this variable logic state. So if Q equals a 0, Q2 equals 0, Q1 equals 0. If Q equals a 1, Q2 equals 0, Q1 equals 1. If Q is a 2, Q plus 2 is a 1 and Q1 is a 1. Okay. So, like I said, we're going to implement this with two binary JK flip-flops. So this is JQ2, KQ2, JQ1 and KQ1. So if, say, Q2 equals a 0 and Q2 plus is a 0, 0 to 0 is a 0, J is a 0 and K is an X. Yeah, and J is a 0 and K is an X. And say if Q1 is a 1 and Q1 plus is a Q1 is a 0 and Q1 plus is a 1, is a 1x. So here JQ1 is a 1, KQ2 is an x. So that's how you generate the binary inputs for J and K for the two binary JK flip-flops. Okay, now we'll move over to the Kanalugh maps. This is JQ2 at the top here. So when T2 is a 1 and T1 is a 0, is a can't happen state. So for this row, these are all x's. So there's 12 rows of the truth table, and it's these group of 4 here, this one. So this is a sum of products expression. This loop here is not T2 and T1 and Q1, and this loop here is T2 and not Q1. So we all the terms together, so we get JQ2 equals not T2 and T1 and Q1, or T2 and not Q1. For KQ2, the same rule apply. T1 is a 1 and T2 is a 0 is a can't happen state. So we're only dealing with these 12 coordinates of the Kanalugh map. This is product of sums expression where there's only one sum term, and this is T1 and not Q1. So KQ2 equals T1 or not Q1. Here we have the flip-flop Kanalugh map design for flip-flop JQ1. This is input JQ1. This is a product of sums expression. In this case, there is only one sum term, which is this loop here. I will loop in the zeros, and this loop equals T1 and Q2. So JQ1 equals T1 and Q2. Here we have the input for KQ1. Same deal here. T1 equals 1 and T2 equals 1 and T1 equals 0 is a can't happen state. So we're just dealing with these 12 coordinates of the map. And this loop here is not T2 and T1 and Q2. And this loop here is T2 and not Q2. So KQ1 equals T2, not T2 and T1 and Q2, or T2 and not Q2. Here we have the T-type flip-flop circuit diagram. Here you have the ternary input T, and we convert it to binary here. So these are the binary components, not T2, T2 and T1. Here we have the output. This is the ternary output Q and the ternary output Q bar. So if Q was to cycle 0, 1, 2, Q bar would cycle 2, 1, 0. So it would be the opposite of, if this counted up, then Q bar would count down. Now clock is binary, and the set and reset inputs are binary. I've just provided a pull-up resistor there, so you don't have to connect them if you don't wish to. Now JQ2 is this input here. That's a 3 input AND, 2 input AND, and a 2 input OR. These are 2 input ORs here for this one, for KQ2. J1 here has a 2 input OR, and KQ2 is a 3 input AND there, a 2 input AND there, and a 2 input OR there. So the outputs from Q2 and Q1 and not Q1 and not Q2 are fed back here and form part of the input variables, along with T2, not T2, T2 and T1. Okay. I'm going to move on to the JK flip-flop. This is a characteristic equation again of Q plus equals J plus K plus 1 times by Q and plus J. Again, if you look at my previous video on base N JK and T flip-flop, it'll explain how we derive this equation. But all calculations are done here, modulo 3. So this is JK and Q, it's Q plus, and the truth table follows the characteristic equation. Q plus equals J plus K plus 1 plus times by Q plus J. This is the ternary variables here, the four ternary variables, and these are the binary variables here. We're going to implement this again with two binary JK flip-flops. So we have JQ2, KQ2, JQ1 and KQ1. They're the inputs of JK to the binary JK flip-flops. And here J2 and J1, K2 and K1 are the ternary, well, the binary coding for the ternary inputs J and K. So don't get them confused. Okay, so J2 and J1 are the binary codings for J, and they follow the coding if J is a 0, J2 is a 0, J1 is a 0, if J is a 1, J2 is a 0, J1 is a 1, J is a 2, J2 is a 1 and J1 is a 1. Similar for K. So, K is a 0, K2 is a 0, K1 is a 0, K is a 1, K2 is 0, K1 is 1, K is a 2, K2 is a 1, and K1 is a 1. Same coding for Q plus. If Q plus is a 0, Q2 plus is a 0, and Q plus 1 is a 0. If Q is a 1, Q2 is a 0, Q plus is a 1, Q1 plus is a 1. If Q plus is a 2, Q2 plus is a 1, and Q1 plus 1 is a 1. Now again, for the same reasons as before, Q1 and Q2 have four codings for 0, 1 and 2. If I can show you the second half of the truth table. Here, when Q is a 1, Q plus is a 1, which doesn't follow the characteristic equation. This is because if Q1, Q2 and Q1 starts up in a 1, 0 pattern, on the next clock cycle, Q2 plus and Q1 plus start off with a 0, 1, which is also a logic 1. A ternary logic 1, sorry. From then on, Q2 and Q1 follow the same codings as JK and Q plus. Now, the excitation, I haven't shown you the excitation on this particular one, but for JQ2, KQ2, JQ1 and KQ1, if Q2 is a 1, Q plus is a 0, Q2 plus is a 0, you get JQ2 is an X and KQ2 is a 1. And if, say, Q1 is a 0 and Q1 plus is a 1, you get JQ1 is a 1 and KQ1 is an X. In this case, an X means it can either assume the value of a 0 or a 1. So, going back to this, Q plus follows this characteristic equation. So if Q is a 0 here, this is a 0, then Q plus equals J. So Q plus equals J while Q is a 0, and then from then on Q plus follows this equation down here. Now we come to the Kanalugh maps. This is JQ2. This is a 6 variable Kanalugh map, and you loop symmetrically about the horizontal and vertical. So this loop here is not J1, not K1, and K1 and Q1. This loop here, loop of 4, is not J2, J1, K2 and Q1. This loop of 16 here is J2 and not K1. And this loop of 16 here, which are linked, is J2 and not Q1. So this is a sum of products expression. This is a sum function, the OR function. I should point out that sum of products mean logical sum and logical product, and not modulo sum and product. So this is the expression, these terms are all together, and I'm going to implement this using NAND equivalent circuits for the simple reason you can't buy a 4-input OR gate, but you can buy a 4-input NAND gate. So I'm going to implement this with NAND gates. This is the Kanalugh map for KQ2. This is a product of sums expression. In this case there's only one sum term, which is K1 and not Q1, and you're looping the zeros in the loop. So KQ2 equals K1 or not Q1. This is the Kanalugh map for JQ1. And again, it's a product of sums expression. In this case, there's only one sum term, and this is a loop of 16 here, and that is equal to J1 and not Q2 and Q2. So JQ1 equals J1 and Q or Q2. This is this Kanalugh map for KQ1. This is a sum of products expression. So here we have a loop of 16 here, which is not J1 and K2. We have a loop of 4 here, which is not J2 and J1 and not K1 and not Q2. We have a loop of 16 here, which is K2 and Q2. And we have a loop of 4 here, which is J2 and not K2 and K1 and not Q2. So these 4 terms are ORed together, and again for the same reasons as before, I'm going to use NAND equivalent circuits to implement this expression for KQ1. For the simple reasons, as I said, you can't buy a 4-input OR gate. So this is the circuit diagram for the JK flip-flop. This is the input J, this is input K, SR, set and reset as before in the T-type flip-flop. Clock the same as in the T-type flip-flop. Both the clock, the S and the not R, not S and not R, not set and not reset are binary. We included pull-up resistors so you don't have to connect anything to S and R. You've got Q here and Q bar as before, as in with the T flip-flop, and have the variables not J1, J2, J1, J2, not J2, K, not K2, K1, K2, not K2. There. So they're the binary coded variables for K, they're the binary variables for J. So I've implemented these sum of products expression here using NAND equivalent circuits. There's a 4-input NAND, and these are 2-input NANDs. There's a 2-input OR, and again I've done the same with KQ1. These are NAND, 4-input NAND circuits. gates, and these are 2 input NAND gates. So if you don't understand how I've done these circuits, converted ternary to binary and then converting binary to ternary, please watch my video on binary implemented ternary logic circuits, and that'll explain it in more detail. Right, I think that concludes the presentation. Hope you'd enjoyed it. Thanks for watching. Bye.